I frozen. Okay, this is 20/3. Now, these problems, they're just like this on the test. They're just like this on the AP exam. Okay, what did you get for the first series? I know what you got. 2/9 plus 1/4. Who cares? 17/36, is that what you said? Okay? Yes. Maybe somebody want to come up and do this one? If I do this first one, they're both the same, I'm going to pull the 2 out. My problem with this, first you have to recognize it's geometric. So, it's S equals A over 1 minus R. Now, I'll write out some of the terms. Let's see, 1/10 plus 1/10 squared plus 1/10 cubed. Hey guys. Shh. James? Justin? Okay, what's A? A is where you start. What's the common ratio? 1/10. Justin? Okay, so it's 2 times, now, it's A, which is 1/10, over 1 minus a tenth. And if you don't want to deal with fractions, then what we're going to do is we're going to multiply by 10 over 10. Because then it's easy. I don't have to deal with those fractions. So this is going to give me 1 in the numerator and 10 minus 1 in the denominator. There it is, 2/9. You're going to see problems like this on the exam. Okay, Matt? Is this okay? Now, some of you attack this one by doing partial fractions. What's the very first convergence test? Take the limit as n goes to infinity of n squared over 3, and that's n squared plus 3n plus 2. That's going to behave like n squared over 3n squared. What's that limit? 1/3. Make sure you understand what you're doing. It diverges because the limit of the sequence must be 0. So that was an easy problem. So we just tend to jump right into the convergence test rather than looking at the limit of the sequence. Keep the difference between the sequence and the series. The 12 days of Christmas is a series. On the first day, you get a partridge in a pear tree. On the second day, you get, unless I sing it, turtle doves? 2 turtle up. Okay? How many partridges do you have on the second day? Not 1, 2. And how many turtle doves? You get 2. What about the third day? So you have 3 French hens. How many turtle doves now? Nope. You get 2 twice. You get 4. Because remember, you get this, each day you get them again. And now you're at, what, 3 partridges. You want to hear me sing? Come to my concerts next weekend. It's a Sunday. Well, I don't have a solo, but next. December 10th. Okay. And actually, I can start to sing now. Okay, guys, this is a little tough. Okay, guys? Okay, ready? We're going to get to the integral test. And some things I'm going to hit on lightly because we did a lot of it yesterday. Okay. I want to compare 1 over n squared to 1 over x squared. Now, I graphed 1 over x squared. 1 over n squared is just the dots. So it's 1. Now, what I'm going to do is find the areas of these little rectangles. And the question is, do I want them to be inside rectangles or outside rectangles? I don't know. I don't know. You want them to be inside. Okay. Does 1 over x squared converge? Well, how do you know? If you did the homework, uh, you should have some idea. Remember, this was the integral of 1 over x to the p. And remember that this converged was p was greater than 1. We did that yesterday. Otherwise, you could integrate it. You need to be able to integrate it. So does this converge or diverge? Okay, it converges. And in the book, they do this method, but the author doesn't explain why he chooses the underestimates or the overestimates for these little rectangles. If I want to compare 1 over n squared to this converges, what do you think is going to be true about 1 over n squared? It's going to converge. If I do rectangles that are over that, does that really tell me anything? It's bigger than something that converges. The author never discusses that. He just puts them underneath and you go, why did you do that? So let's do that. Let's put these underneath, because if this area under here is less than the area under the integral and the integral converges, then this is better converge. So what is this area here? Now we're integrating from 1, so I'm going to have to play with this a little bit. But this area is 1, because this is 1 and this is 1, right? Plus, and then this base is 1, and the height is going to be a half, right? Plus 1 times a third. Plus 1 times a fourth. There's the harmonic, sorry, it's squared. So the harmonic series doesn't converge. And we'll say, wait a minute, there's the harmonic series. I know it doesn't converge. Okay, so that's, we want to compare it to this. Well, what I'm going to do is it's less than or equal to 1 plus the integral from 1 to infinity. Because the integral only goes from here. So what I'm going to do is add a 1 to both sides. So I've got this one there and that one there. And then you could subtract them. But can you see that all of this then is going to be less than that? All the 1 does is shifts my convergence up by 1. That's it. That's not going to change it, is it? This is still going to converge, right? So the 1 isn't important. So do you believe that all of this is underneath the convergence series? If I try to do on the outside one, I can. It just doesn't do me any good. That's all. So if the integral converges, then the series converges. That's the integral test. And you might say, well, why don't we just always use the integral test? Because not everything can be integrated. That was my question, too. Let's look at the next one. That was just a little extra ones there. Now, is this going to converge? Now, remember, we had this integral from 1 to infinity of 1 over x to the 1/2. That's what this is. Does that converge? We talked about that yesterday. Does that converge, David? Remember, 1 over x to the p from 1 to infinity converges when what? P is greater than 1. We have to know that. We have to know that. We're going to do that today, too. We have 2 things we're going to do. Integral test and the p series. So this is going to converge or diverge? It's going to diverge. Now, if I were to put my little dots here, I'll put my dots in. Now, this is 1 over the square root of n. I don't care exactly how big it is. And if I do the inside rectangles, is that going to tell me anything? This diverges. If this is smaller than a divergent series, am I going to know what happens? Nope. So this time now I want to do the rectangles that are on the outside. So I'm going to do this rectangle and this one. So if I can show that the area of these rectangles is bigger than the integral, and the integral diverges, then what's got to be true about the areas of my little rectangles? They have to diverge. What is the area of this first rectangle? It's 1 times 1 over the square root of 1. Right? And I'm going to get the series out of it. And it's 1 times 1 over the square root of 2 plus 1 times 1 over the square root of 3. I'm just finding the areas of these rectangles. What's the area? This is the base is 1, and this is 1. This height is, 1 over the square root of 2 is right there. I'm finding the areas of these rectangles. But do you recognize what the left side is? Clearly, this is bigger than the area, remember an integral is an area from 1 to infinity of 1 over x to the 1/2 dx. But what is this? This is the summation of 1 over the square root of n. And n starts with 1 to infinity. If I were to write out the terms of that series, that's what I get. I'm just using areas to show it. So all I'm trying to do is justify the integral test. That's all I'm trying to do is if the integral converges, the series converges. And you want to be filling out your little study packet as we go. You don't want to do it the day before the test. If the integral diverges, the series diverges. I chose the outside rectangles to look at it because the inside ones just don't tell me anything. Yeah, this diverges, big deal. This is smaller than a divergent series. It could diverge, it could converge, which actually gives me a little bit in the comparison test. Now, you don't have to know the justification. All you have to know is the integral test. And I think I have it formally written up here. Now, here's the thing. You really need all of this. My function has to be continuous, has to be positive, it has to be decreasing from 1 to infinity. So the problem with factorials is they're not continuous. Can't integrate a factorial. So I'm kind of stuck there. And it's wordy, but that's the only way you can say it. The series a sub n converges if, it's if and only if, the improper integral converges. So basically this is what you have to know. If the integral converges, the series converges. If the integral is divergent, the series diverges. No, you'll never have. All I was doing was looking at, let's go back, just let me try and hit it. I know everybody has problems with that. I want to see, we know that this diverges, right?
Yeah.
This is the series associated with it. I'm just trying to justify the integral test. And I think you believe it. That's not an issue. But this, what's an integral? It's the area under the curve, isn't it? So if I do the area under this curve, it's all of this, right? And I know if I add that up, it's divergent. So then I'm going to take the area formed by using the little dots here, and I'm going to take the outside rectangle. So what's the height of this rectangle on the first one? It's 1, and the base is 1. What's the height here? It's, well, it would be half. It's 1 over the square root of 2 times 1. What is this when I add them up? It's the series. So the area here is the series. And I know that this area is bigger than that area, so this series is going to be bigger than that one. That diverges. So what has to be true about this one? Has to diverge. Could I have taken the inside rectangles? Yes. And I would have said that these all add up, and they're less than the divergent series. Less than the divergent series, I don't know anything. And you're going to find that in the comparison test. Almost tempted to do it today, but it's not on today's lesson. It's in this section. And all we're going to do is work on integral tests and p-series. We haven't done the p-series, but you'll like that. Everybody likes that. Okay, so is that series convergent or divergent? Pardon, is that series convergent or divergent? Well, let's find out. We're going to use the integral test. So on the homework, I hope I have it set up right. It should be just integral test problems. The problem's going to be when they're all mixed up, and you have to figure out which test to use. That's the problem. So the function is from 1 to infinity. It's the log of x over x. Now, why did we do the improper integral? So I could do this today. So if you didn't practice it, you may have problems. We're going to do u substitution. What's the u going to be? Okay, so I'm going to ignore the limits of integration to begin with. So it's du. 1 over x dx. I tend to recognize the 1 over x dx. You could solve for dx like Justin did. There's nothing wrong with that. It works. But there it is. That's equal to what? That's just du. So I have the integral, and it's going to be, this is u, right? U, and the other part is du. So let's go ahead and integrate that. Then let's switch it back to x, and then we'll do our improper integral. So what's this equal to? U squared over 2. So I'm going to, excuse me, I don't know what they're doing. Okay, so this limit from t to infinity is going to be u squared, but what's u? ln of x. And we're going to evaluate this at 1 and t. Are you okay with that? There's no smooth way to do this. Pardon? Thank you. Well, I don't even need the square because what's going to happen? The limit as t goes to infinity, and it's going to be the log of t squared over 2 minus the log of 1 squared. What's the log of 1? So that's 0. And what happens? James, what happens here? Let's pay attention. What's true about the log of t? It goes to infinity, right? So this is divergent. Because when you let t go to infinity, this is getting infinitely large. Has to go to a number. Okay? By the way, what's the limit of the sequence as n goes to infinity? This is something you should put in your notes. What is that limit? Which is bigger? The denominator is bigger. This is 0. You're going to see some of these things come back, and you're going to say, oh, I don't know which way it is. You will. Trust me. I made a u substitution, and I said this was u, this is du, and then an antiderivative was u squared over 2. You have to, don't forget to find the antiderivative. Yes, n is larger than natural log of n. Then what happens if I do a reciprocal? What happens to the inequality symbol? Do you know? It switches. You're going to see these. I'm telling you, you're going to see them. So, okay, ready? That's the integral test. Okay, I'm not going to go through this because you know what? We did this with the integral, didn't we? What if p was less than 0 on the integral? X to the p, remember when we did that? I don't want to do it again. It diverges, right? What if p was 0? Remember from yesterday? Diverges. What if p is less than 1, bigger than 0? Diverges. But if p is greater than equals 1, it diverges. That's 1 over x. You can do the integral test if you'd like. We did it. We did the integral test. What's this one going to be? P is greater than 1? Converges. So, the series, this one, n equals 1 to infinity of 1 over n to the p, converges for p greater than 1. It's called the p series. Yes. Yes. Kevin, you gonna know how to do this?
How do you draw that little squiggly line really well?
The summation?
Yeah.
I don't know, 50 years of doing it? Okay, it hasn't been 50 years of doing that. I'm not that old. Not that old.
I will not be doing calculus for 50 years.
You're a teacher, you might. Wait, what are you gonna be?
Well, calculus. Engineer, physicist.
You'll be doing calculus. Engineers do nothing but calculus. Okay. Doctors don't do calculus. Okay. Okay, guys. Now, wonder why. Notice you have the P series. We have 2 tests now, 2 new tests. We have the integral test. What does the integral test tell us? If you integrate, if the integral converges, what's true about the series? Series converges. They do the same thing. If the series integral diverges, guys, and then you have the P series. So we could look at problems right directly out of that homework. I don't even know what I've assigned, but I don't think that 1 through I don't think that's right. Yeah, questions. You want to look at that again?
Yeah, I just want to look at
I'm just trying to justify the integral test.
Wait.
There are two ways I could draw my rectangles: over and under.
Yeah, it's not all.
This is equal to, this is this, which is this series. And it's not less than the integral. I have to add the 1 in there to make it less than that. It's not balanced. Because this has this area. The integral is just this. So I just added 1 to that, which doesn't affect the convergence or divergence at all. Now, are there questions still on 8.3? 8.2, I mean. Or any questions? We have a quiz. You guys, you all have a calendar. If you don't, I got more. Okay, guys, Monday we finished 8.3, which is going to be the comparison test, the limit comparison test, which isn't too bad. Then Tuesday we will do the others, last 3 tests. We'll be up to 7 then. Okay, so we're at 5 right now. 2 more on Monday, got to know them all. And I just kind of go in order. I put it to the 12 days of Christmas. And the lyrics should be online. I can print them up if you want. On the first day of Christmas, my true love gave to me the fact that the limit's not equal to 0. I can't get it to rhyme, but the rest of them work pretty well. Okay, and then we have a quiz on next Thursday, the 8th, 8.1 through 8.3. It's a regular quiz. And then on the 9th, we review, and on Monday, the 12th, I'm testing all day, you're testing on 8.1 through 8.4. 23rd, yes. No, 22nd. Then we'll do 8.5, and you guys really have to do 8.5 and 8.6. And then we'll test on that. And then after break, we'll do the Taylor polynomials. Yeah, well, those are even more important. A lot of people still aren't doing the homework. Okay, I need to come around and check off your homework for 8.2. I know. Somebody did give it to me. But, okay, do you have any questions or you're going to work? Where's your book?
I actually don't work. Don't we just set today this week?
Pardon? No, you guys, you need to work in class because this is hard.